Good morning, everyone. I don't know how I got the privilege of going first, but I'm grateful to be here. If for those of you who don't know me, I'm Michael Fischer. I joined the faculty last year, and a lot of my work focuses on hurricane structure and intensity change, especially rapid intensification. And I'm going to use rapid intensification, I think motivates the topic of today's talk. So why do we care about rapid intensification, or at least why do I care about it? There's two main reasons. Storms that undergo rapid intensification quickly become more dangerous by definition, as destructive potential of a hurricane scales nonlinearly with storm intensity. And the second part is that TC intensity errors are relatively large in these RI events. And so what you see in this figure here is the official National Hurricane Center intensity forecast error average over the last 5 years for all cases in the black line, non-RI cases in the blue line, and specifically rapidly intensifying storms in the orange line as a function of lead time. And so we can see that these rapidly intensifying storms have average forecast errors that are 2 to 3 times larger than their non-RI counterparts. So we have this double whammy of storms quickly becoming more dangerous, and to top it off, they're not as well forecast. So not ideal. So what's going on with these RI storms? Why are they not well forecast, and what do we know about them? One of the main tools we have are statistical and machine learning models to forecast rapid intensification. And these models largely use information about the storm's environment. We know from the literature that storms tend to undergo RI preferentially in more favorable environments, so environments with weaker vertical wind shear, warmer sea surface temperatures, and a more humid atmospheric column. But it's not as clear how the vortex structure relates to rapid intensification. Are there favorable configurations? Could lead one to ask, are these rapidly intensifying storms associated with unique vortex and convective characteristics? And when I say lead one to ask, I mean, at least I asked this question in this paper that came out last year. And spoiler alert, yes, these rapidly intensifying storms are associated with unique vortex and convective characteristics. More specifically, storms that undergo rapid intensification tend to have anomalously tall vortices and anomalously more narrow vortices compared to storms that slowly intensify or don't intensify altogether. So knowledge of the vortex structure can provide useful information in forecasting rapid intensification. So how did we find these results, and how do we identify vortex structure in real time? Probably our most useful tool we have is the tail Doppler radar on board NOAA's P3 and G4 aircraft. I have an animation here of what these observations from the tail Doppler radar look like. So this is a case of Hurricane Dorian. On the left, you see a plan view of the wind speed at a height of 2 kilometers in the lower part of the atmosphere, and the right is a vertical cross section taken along the flight track. So the tail Doppler radar basically provides us a CAT scan of the three-dimensional hurricane structure. And as you saw from the previous slide, can provide useful information for short-term intensity change. And so these observations are actually used real-time, transmitted to the Hurricane Center, and used in our operational hurricane models. And assimilating these observations can improve the forecast skill of the models by about 20 to 30%, some previous work has shown. So NOAA's been flying now for decades, collecting these observations, and I've helped build a database called TC Radar, the Tropical Cyclone Radar Archive of Doppler analyses with recentering. No one wants to say all that, so we just call it TC Radar. And now we have over 1,500 unique analyses from pre-Genesis systems all the way up to Category 5 hurricanes. These observations are primarily collected in the Atlantic Ocean, as you can see here. And there's been a few flights in the Eastern and Central Pacific. But we know that tropical cyclones are a global phenomenon, and they don't just occur in the Atlantic Ocean. So there's these very large gaps that exist spatially and temporally where we don't have these useful tail Doppler radar observations. So this creates somewhat of a challenge. But on the flip side, although we don't have tail Doppler radar observations everywhere, we do have geostationary satellite observations. So can we use machine learning to learn the relationship between the storm's appearance on geostationary satellite imagery and its three-dimensional vortex structure? And if you give a talk of machine learning, you have to use an AI-generated image to help you with the flowchart here. So basically, can we take an IR snapshot, train a machine learning model, and can it spit out the three-dimensional vortex structure? So we're going to do that here using a model that I call the Tropical Cyclone Synthetic Wind Analysis using regression models, because I like acronyms, and we're going to call it TC Swarm. And TC Swarm, it consists of 4 main inputs that go into the model, 4 categories of inputs. The first being information about the infrared brightness temperature field. The second is basically how does that IR field map relative to the low-level storm center. The third group is information about the storm's environment, wind shear, sea surface temperatures, things like that. And the fourth, I kind of cheat here a little bit by giving it the best track intensity, but this is not directly telling it, what is the structure of the storm. That's what we're really interested in, not just how strong the storm is, but, is this an anomalously tall vortex, anomalously narrow vortex, as we saw before. So this information is fed into two upstream machine learning models, one that predicts the vortex tilt. So for those of you who don't know, a hurricane's not always vertically aligned. It can be displaced in the vertical or sometimes totally decoupled. And the second upstream model is one that predicts the radius of maximum wind. So basically, do we have a really compact inner core, or do we have a really broad or diffuse vortex? All of this is fed into then our main TC swarm model, which is a gradient boosting regression model that allows us to estimate the full three-dimensional wind field. And before I continue, I do want to give a special shout out to three very talented undergraduates here in our program, William Bouza, Deelan Jariwala, and Matt Reardon, who helped me develop especially the vortex tilt model, but Matt also worked with me on the radius of maximum wind model. Okay, so TC swarm, what are we training it on? How do we get the output? Basically, I'm giving it SHIPS environmental data. For those in the hurricane community are familiar with that. I'm using NASA has this merged IR gridded database, globally gridded IR fields available every 30 minutes. So we can get an IR snapshot plus or minus 15 minutes from the time of the TDR analysis. And I'm using 2000 to 2022 as our training data set and a validation data set of 2023, and then a totally independent testing data set for 2024. So I've now yapped a lot about rapid intensification and machine learning model and training and the workflow. What does this look like? So I'm going to apply this to the case of Hurricane Beryl. The left is the original TDR observations. The right is the machine learning analysis. The model doesn't know anything about this storm, but it's estimating what the wind speed is here at a height of 2 kilometers. So you can see that there's pretty good agreement. We see a similar value of peak wind speed. We see similar asymmetry, stronger winds in the northeast side of the storm, weaker winds in the southwest side, a similar radius of maximum wind. And the nice part about this machine learning analysis is you're not confined to the logistics of the radar system. We don't just get this swath of data 50 kilometers on either side of the flight track. Now we can get a much more full field. And so this is a qualitative comparison, which seems the machine learning model is doing good. We can do a more quantitative assessment for this same case of Hurricane Beryl. So the top left is that same IR snapshot, now with colors. The middle is the observed wind field with wind barbs overlaid, and the right is this machine learning analysis. We can do a difference plot on the bottom left here. So observed minus the machine learning analysis, where you see red colors. That means that the observed wind speed was stronger than what the machine learning model said. So on the northeast side of the core, the machine learning model kind of underestimated the wind speeds. And in the southwest part, the machine learning model kind of overestimated the wind speeds. But nevertheless, if you do a one-to-one plot where your observed winds are along the y-axis, and the machine learning analysis is on the x-axis here, you can see there's pretty good agreement. The correlation is 0.97. So that means the machine learning model is doing a good job estimating the structure of the storm. And another way of looking at it is you can take these azimuthally average wind profiles. So basically at a given radius from the center of the storm, you average the wind speed of all these grid points. And you can see that the peak wind speeds are occurring at a similar radius, about 20 kilometers or so. And the rate of decay of the vortex outward is similar. It's slightly too slow in the machine learning analysis in this case. But you can say, Michael, good job. You cherry picked this nice case with a well-defined eye. It's easy to do. What does this look like in other cases? It still can do well even when we don't have a well-defined eye. In fact, it arguably did even better in this case. This is Milton when it was undergoing rapid intensification in the Gulf. You can see there's no eye present in the IR snapshot on the top left. Although the correlation is slightly lower 0.91, the domain RMSE is 2.3 meters per second. For reference, the observational uncertainty is 1.5 meters per second or so with the TDR system. So we're on the order of observational uncertainty with this case. So this is a really good case. What about some other storms? We're interested in, right, in other things like storm size, for example. Here now I'm comparing the case of Hurricane Helene when it was in the Gulf. This was a very large storm, a record large storm, in fact, compared to Milton on the bottom row here. Both of these storms had the same intensity at the time. They were Category 4 hurricanes, maximum winds of 120 knots. But you can see from the machine learning analysis on the right column here, the model correctly captured that Helene had a much broader vortex, much stronger winds extending farther away from the center of the storm than the Milton analysis, which was much more compact. So this is useful, right, for things like forecasting storm surge, for example, or other hazards, where surge is closely related to the size of the storm. Larger storms tend to produce bigger storm surges. So this could hopefully provide useful forecast guidance in the absence of aircraft reconnaissance observations, maybe even for basins where we don't have routine reconnaissance. So what does this look like across the whole testing set? So we had about approximately 200 independent cases that went into our 2024 evaluation set. Again, this is just for a height of 2 kilometers here. For reference, again, our observational uncertainty is 1.5 meters per second. So on average, our mean absolute error was about 4 meters per second, and our RMSE was 5 meters per second. But the median error was 3 meters per second, so just twice the observational uncertainty. You see the largest errors right near the storm center in the inner core region. And that's because if you get the radius of maximum wind just slightly wrong, because there's such strong gradients, you can quickly get large errors in the center of the storm. So there's maybe other metrics that might be more useful, one could argue in this case. So the model, again, I would still argue with these performance, in the absence of aircraft reconnaissance observations, this would still provide an insightful analysis of what the storm structure was like. I am now yellow. I was going to show that the model is capable of also, not just in the low levels, can actually accurately show vortex tilt and alignment. Well, you can take my word for it. I can talk to you about it after. And I'll just jump to the key takeaways here. So what I'm not trying to say is we don't need to fly and, no, why are you flying for no reason? No, that's still the gold standard. It's very valuable. And you could argue the more we fly, the more data we collect, the better we can make these models. But in the absence of recon, I hope a product like this could be very useful for not just a forecasting perspective, but in my last bullet, what I want to explore next is we could use this platform to theoretically create a global vortex scale reanalysis of all tropical cyclones that we have geostationary satellite imagery from. So basically like from 1980 through modern time. That could allow us then to perform process-based analyses to better understand, how does the vortex structure evolve leading up to the onset of RI and other things. So I would like to thank you for your attention.